This is Dr. Holt. This video is on AP Physics C exam review. The topic is circular orbits. When dealing with circular orbits, you're basically going to be dealing with two equations. The first one is velocity is equal to square root of big G, which is 6.67 times 10 to the minus 11th, times the mass divided by r, and r being the distance from the center of the mass outward, and velocity is equal to 2 pi r divided by period, or you can say that period is equal to 2 pi r divided by the velocity. Now, I'm going to show you a way to derive this equation, so you don't need to memorize that. I think it's the best way because I think it's going to make you understand it better. Here, I'm going to find the velocity to maintain a circular orbit 400 kilometers above the Earth's surface. Now, notice here, I don't give a mass. It makes no difference whatsoever where I have an elephant or a mouse that's traveling 400 kilometers above the surface. It's going to have the same velocity because it's accelerating back at the Earth at the same rate. What I like to do here is to draw a free body diagram. We'll just pick a point right here. If I draw that free body diagram, I'm going to have a force immediately that's coming back, that's trying to cause that's causing this object to accelerate back to the center of the Earth. And that value there would put as big G times mass of the Earth times mass of object 1. We'll call this object 1. And we will divide that by radius squared. Okay, so that basically is the force of the Earth onto object 1. Now the other thing is, if this object has a velocity, which it has to have some type of velocity to maintain a orbit, because as it goes around, it's falling toward Earth. So we're going to find out what this velocity is. What you want to do is take this and just set it equal to mass times acceleration. So we're doing the same thing we always do. Net force is equal to mass times acceleration. So out to the side, again, this is just myself. I like to do this. I'd like to say this is my mass of 1 times the acceleration. The only acceleration I have is centripetal acceleration. Now, centripetal acceleration is defined as velocity squared divided by the radius. So we're going to set this equal to. So all I'm really doing is saying the summation of forces in the y is equal to mass times acceleration in the y. And this time I'll call it ACY because I'm accelerating the y direction. I'm going to let down be positive here. So that's going to give me big G times mass of the Earth, or whatever object you have, times mass 1 over r squared is equal to mass 1 times velocity squared over r. Again, I'm just doing mass times acceleration. That's all I'm doing here. Now look what you can simplify here. I can take away mass here, take away mass here. I can take away r here. I can take away this value here. When I do that, I will get big G times mass of Earth over r is equal to velocity squared. Now we will solve that. I can say that big G times mass of Earth over r square root is equal to v. And to go back, that's exactly the equation that I have here. So again, if you forget it, it's very easy to derive, and actually I prefer you to derive it. Now there's one thing that's a little misleading about this equation. This is assuming that this mass here is very, very small compared to this large mass here. Because technically, note, even though I'm going to exaggerate this, that we're rotating around this point, this object here is causing this object, causing the Earth to want to accelerate back this way. What happens is you get a shift in the what's called the barycenter. And the barycenter, I'm going to exaggerate this substantially. Let's say this point right here. This is, if this mass becomes really, really large, this center of gravity will shift between the two objects. And this equation is not exactly valid, but I'm going to go over a binary system in just a second. Now, the reason you can get away with this regarding, say, the Earth going around the Sun is because of the Sun having such a large mass. The barycenter within the Sun shifts, or the center of mass, which is called the barycenter, just shifts very, very small away from the center of mass of the Sun. So it's not perfect, but it's very close. So this equation for like satellites and things that have small mass, this works fantastic. All right. So again, if you get this velocity and then you want to get the period, just go back and say that 2 pi times the mean radius divided by the velocity, that will give me the period. And again, all I'm doing is using this equation right here. Just manipulate that. All right. So that's how you're going to use this equation here. We're going to actually find out what the velocity to maintain a circular orbit 400 kilometers above the Earth is going to be. So to work that problem, give myself some space. I'm going to use this equation which I've derived, and all I have to do is plug values in, and I'm going to say square root of 6.67 times 10 to the minus 11th. And again, I'm leaving units out, times the mass of the Earth. And we said the mass of the Earth was 5.97 times 10 to the 24th kilograms. And we're going 400. Now you cannot use the 400. You got it. You're going from center here all the way up to here. So we need to include the radius of the Earth. So we know the radius of the Earth is approximately, let's say, around 6371. So we will take 6371 kilometers. We'll add it to 400. We'll multiply that times 10 to the third. And then so we got that perfect. I'll put another set of parentheses in there, just like that. We will calculate that value there. And I believe if you run that number, you're going to get the velocity is going to equal to 7668, I believe, meters per second. So again, that's going to be the velocity to maintain something in orbit, like a satellite or something that has a small mass. All right, I'm going to work a problem now that's a little bit more complicated, and it's going to be what's called a binary star system here. And this is actually quite interesting. I have a binary star system, and then binary star systems do exist in the universe. It's where two stars are rotating around the other. And actually, we have systems where we have three stars rotating around each other. So here I have a different mass. I have 2.5 times 10 to the 30 kilometers, and I have 2 times 10 to the 30th kilometers. Now, we know exactly that if the masses were the same, then I would have, I'm going to draw this little circle. We would have the center mass to be right in the middle. But since this has a greater mass, this value center mass is going to shift. So what's going to happen is everything is going to rotate around what's called this new barycenter. And we're going to calculate what that would be. Now to calculate that, just go back and do the center mass equation, and we'll find out what that is. And we know that x bar is going to equal to mass of A times its x bar, we'll call it x bar distance, plus mass of B times its x bar distance, divided by the summation of masses. So it'd be mass A plus mass B. Okay, so I'll put the real numbers in, and to do that, I will get x bar is equal to, what's that, 2.5. 2.5 times 10 to the 30th, and that's x bar is 0. I'm going to take everything from this point right here. So I'm establishing this as like my neutral point, or my 0, 0 point. All right, then I will do plus 2 times 10 to the 30th times the distances away, 1 times 10 to the 10th. Again, I'm neglecting my units here, so please make sure you get the units correct. I will add it to 2.5 times 10 to the 30th plus 2 times 10 to the 30th. I will calculate that value, and when I do, I will get x bar is equal to approximately 4.44 times 10 to the 9th. So that means that this distance from here to here is going to be 4.44 times 10 to the 9th, which means this distance here is going to be 5.56 times 10 to the 9th. Let me clean that up a little bit. It looks nasty. All right. Now, you cannot just go back and use this equation, because this equation, again, is only valid when one mass is very, very small compared to the other one. All right, so now what I'm going to do is basically I'm going to create another free body diagram. Again, live and die by these things because these free body diagrams will help you solve all these problems. I'm going to draw a free body diagram of mass A. So I'll have this force here. And we're going to call that the force of B onto A. And to run that value, now here, we're going to be doing the big G. We'll do 6.67 times 10 to the minus 11th times the two masses, 2.5 times 10 to the 30th times 2 times 10 to the 30th over r squared. Now to do r squared, you want to do the distance they are apart. Okay, you're not going to do these values here. I'll show you in just a second. You're going to take the distance they are apart and find what the force of attraction is between the two. That's going to give me 1 times 10 to the 10th. We're going to square that. We're going to run the calculation. We will find that the force of B onto A is going to give me a value of approximately 3.335 times 10 to the 30th newtons. Now obviously the force that A onto B is going to be the same thing but going back the other direction. Okay, now what you're going to do is you're going to set this up like we did, how I worked this problem before, is set the force and set it equal to mass times centripetal acceleration. So again, I'm going to take this force of B onto A. I'm going to set it equal to the mass of A times velocity squared and divided by the radius. Now this is where the radius plays in. You're going to use this radius right here because everything's rotating around this point right here. So we'll put those values in. That's going to give me a value of 2.5 times 10 to the 30th times v squared divided by 4.44 times 10 to the 9th. I will set that equal to 3.335 times 10 to the 30th. I will solve for v. And when I solve for v, I get a value of approximately 76,960 meters per second. Again, that's only for the velocity of A. These binary stars are going to be traveling at different velocities. Okay, so that gives me a velocity of A. Now to find the velocity of B, I go back, basically do the same thing, 3.335 times 10 to the 30th times velocity. I should have actually done this too, just so you don't get confused. A. Now I'm going to do velocity of B squared divided by the radius, and now here the radius I'm going to use the 5.56 times 10 to the 9th. 5.56 times 10 to the 9th. Again, I set that equal to my force, 3.335 times 10 to the 30th. I solve for VB, and VB is traveling about 96,504 meters per second. Okay. Now, if you want, for the heck of it, you can find out what the period is. Now, what you're going to notice too, the periods have to be the same. So to find the period, I go back to T is equal to 2 pi times I velocity. And remember, these are velocities, these are average velocities. So if it's going in a circle, this will be this constant. So I will take velocity of A. Oh, I'm sorry. Change that. Sorry, I'm going to take the radius of A. I apologize for that. 2 pi r. So we take the radius of A. I will put the value in as 5.5. Oops, sorry, 4.44. Sorry about that. Got to do this right. 4.44 times 10 to the 9th. I would divide that by the velocity of the 76,960. And when I run that value, and then it's going to give you the value in seconds. And I went ahead and converted the seconds to days, and I got approximately 4.19 days. Now, if you do this again for doing the other one, all you have to do to find the period, again, this is the period of A, to find the period of B, you just take 2 pi times the distance, 5.56, times 10 to the 9th, divided by the velocity of 96,504. Run it again, you're going to get your number in seconds. I get about 4.19 days. Do that red. Now note, I did this for a binary star system. They don't have to be star systems. You could do this for anything. But again, when we do it comparing the Earth going around the Sun, the only reason we don't follow this approach is because if we got X bar, it would wouldn't make much difference, because if we're comparing, say this is the Sun and this is the Earth, we would find immediately that the barycenter is somewhere really, really close to the center. So it's easier to go back and use just this general equation, which is pretty accurate, but it's not precise. By finding the center of mass, you're going to get a very precise equation. All right, I hope this video was useful. Again, this is on circular orbit. Follow the techniques. Again, my preference, I think, is easier to derive this equation. You can do it very quickly. Again, by just setting the gravitational force equal to mass times centripetal acceleration. Anyway, I wish you guys the best of luck.